started with nature of molecules. All right. So first unit, nature of molecules. A lot of this should be review. So if you know it, great. If you don't, better bone up on it because it's the foundation of biology, biochemistry. All right. So nature of molecules, atomic structure. You should know protons, neutrons, and electrons. Of course, you know protons exist in the nucleus, okay, which is ultra dense. All right, where most of the mass is. Because protons and neutrons both have a mass of 1 atomic mass unit, whereas an electron is essentially about 1,800 times less than that. So when you figure out the mass of an atom, you don't even worry about the electron. It's the proton and the neutrons you are concerned with. Of course, protons and neutrons in the nucleus, and then the electrons are in these clouds around it. All right. Clouds, or actually energy levels, is more beneficial in biology. Okay, so first energy level, second energy level. You guys probably recall from chemistry, you can fit 2 electrons in the outer, in the innermost level, and then after that it's 8. So that's why they came up with that what's called the octet rule. Most molecules will react. Okay, or elements will react in order to get that outer shell filled with electrons, and that's generally 8 electrons. First level only takes 2. All right. Let's make a little drawing here. This will just kind of motivate you, I think, a little bit. All right. Atomic number. Atomic number is the number of protons in a atom. Okay, that's the definitive thing about it. Atomic mass is the average masses of all the isotopes for that particular element. All right. So, for example, carbon exists in at least 2 isotopes, C14 and C12. Okay. So carbon has an atomic number of 6. Excuse me, it's got 6 protons. Okay. And so its atomic number is 6. It's got 6 neutrons. Okay, so its mass number would be 12 in this case. Okay. But some carbons have 8 neutrons. Okay, so they're called carbon 14. All right. So when you take the average mass for carbon, it comes out to be 12.01. Okay, which tells you that most of the isotopes are carbon 12, okay, but there are a few 14. Right? So carbon 14 is the unstable one. Okay, so we talk about half-lives and radioactivity. Okay, the most unstable one generally breaks down into other elements. Okay, transmutation. Okay, don't have to worry too much about that. All right, but isotopes are important in biology. Scientists use them as tracers, so they can trace reactions with them by radioactive labeling certain elements and seeing what they do. Okay, they're used in medicine to get pictures. Okay, use radioactive isotope, which then they can trace what's happening inside the body, usually with the in the digestive system. We also use isotopes as in dating things. So C14 is a good example. Okay, C14 has a half-life of about 5,720 years, which means that's how long it takes for half of that isotope to break down, for that isotope to go down in half. So if you start with a certain amount of C14, like in living organisms, after 5,720 years, okay, it'll have half that much. So living things, since they take carbon in from the atmosphere, have a certain percentage of C14, and after they die, they no longer take that in. So you can look at a fossil and compare how much C14 is in that fossil, and they can date objects with that. All right. Periodic table, make sure you're familiar with that. We'll go over that in the PowerPoint, I think, a little bit more. Right. Bonds, of course, forces holding things together. You have ionic bonds where there's a transfer of electrons, and then you have covalent bonds where there's a sharing of electrons. Okay? So in biochemistry, we're mostly dealing with covalent bonds, but there are some ionic bonds, especially in proteins. There's some ionic bonds, which is crucial for the tertiary structures of proteins, which we'll get to. Right? With covalent bonds, okay, covalent bond is a sharing of the bonds, okay, which we'll talk a little bit more when we talk about water. You can have nonpolar and polar bonds. Okay, so a nonpolar would be anything bonded with itself. For example, oxygen is O2. Oxygen is a double bond to another oxygen. Okay, they both like electrons the same, so they share equally. That would be a nonpolar bond. Okay. Something like C and H, they have very similar electronegativities. That means they like electrons about the same amount, so that would be a nonpolar bond. Okay. But if you get something like O and H, which we'll talk about in a minute, okay, oxygen likes electrons a lot more than hydrogen does, so it makes what's called a polar covalent bond, where the electrons are shared but not equally. So electrons spend a little bit more time over there, so this makes this, we use the symbol sigma minus, and then this will be a little bit more positive. So positive, that crosses some polarity, okay, which is pretty important in biological molecules. Okay, now let's talk specifically about water. Okay, water is essential. Okay, a lot of times you could think of humans or animals or any sort of organisms as, like for example, humans as animalized water, because we are chiefly water. Okay, inside our bodies, it's a solvent crucial for reactions. Okay, of course, when they search for life, they search for water, because it's not thought that life can exist without it. All right, so water has some really, really special properties. All right, so of course it's H2O. Okay, so we have oxygen. Oxygen has 6 valence electrons. Okay, so it needs 2 more. Okay, so therefore it can combine with hydrogen, which just has 1 valence electron, and hydrogen, of course, just needs 1 more. So to become stable, satisfy the octet rule. Okay, for oxygen, they share those electrons. Okay, and so they'd have 8. Hydrogen only needs 2, so that it's happy. Okay, so it makes a pretty stable molecule. Again, we talked about polarity before. Every atom has what is called an electronegativity. Okay, so electronegativity is its affinity for electrons. Okay. So oxygen has a electronegativity of 3.5, which is really pretty high. Hydrogen is 2.1. Okay, there's a difference of 1.4, which is a significant enough difference such that it pulls electrons more towards oxygen. Okay, that creates a polarity, a difference in charge. That's why oxygen has a negative charge and hydrogen a positive. Okay, if you just take a drop of water, take a drop of water, put it on this penny, which many of you done before. There, of course, there's millions and millions of molecules of water in there. Okay, and they actually kind of stick together because of the bonds between the water molecules. Right, so I have 2 water molecules here, H2O here, H2O here. They'll align so that the hydrogen on one of the molecules is next to the oxygen for the other, okay, because of that difference in charge. Positive and negative subtract each other, okay, so it creates what is called a hydrogen bond, right? Okay, and that gives that polarity gives that opportunity for the hydrogen bond. Now, hydrogen bond is not real strong, but it's strong enough to have significant impact. Okay? So for example, a covalent bond, depends on the bond, but a single bond usually around 100 kilocalories per mole to break. Okay, so that's your reference point. A hydrogen bond is about 4 kilocalories per mole. Okay, so it's about 20 to 25 times weaker. Okay, but when you take that into totality, it is significant. Okay, those hydrogen bonds, that polarity, bring about most of the properties that water has, which makes water really special. Okay, the first one I have labeled here is a thing called cohesion. Cohesion just means water's attraction to itself. Okay, again, due to the hydrogen bonds. Okay. That's significant for surface tension. Okay, so that's why water leaves will float on water. Okay, which is essential for, of course, photosynthesis. Also responsible for capillary action. Okay, so capillary action is when, like, water goes from the root of a plant to the top of a tree, in the leaf, it gets pulled up by that capillary action. That's water moving through these small little tubes. Right? So the water's attraction to itself allows it to do that. Right? So that cohesion surface tension, okay, can be kind of demonstrated here. Many of you already seen this, but this is just gauze here. Okay, gauze has a bunch of holes in it. And if you put it over a container of water, here's just a jar of water. Okay, if I pour it out like this, okay, nice and like that, it will leak out. Okay, so there's about that much water in there right now. Okay, but if I go quickly like that, you lose a little bit, but it holds. Okay, so water is attracted to itself, and it's also attracted to the strings in the gauze. Okay, and even though there's openings there, okay, it remains sealed. Okay, so that has to do with the surface tension. Okay, in those bonds, adhesion and cohesion. Okay, again, back with the penny. You guys, many of you done this. You put a penny onto a surface like that, which doesn't like water. It beads up. Okay, glass, it does the same. Do this to a cell phone, just on the glass part of it. The water, of course, beads up. Right? So that's due to that the hydrogen bond in there. Right? Also responsible for specific heat. That's an important concept. Specific heat is how much energy it takes to heat something up. Okay, or how much heat it can hold. Okay, so water has a pretty high specific heat. Okay, so therefore it takes a lot of energy for the temperature to go up and down. So it's a real good temperature modulator. Okay, so that's why, let's take the Oregon coast, why it's so cool in the summer is that all that energy from the sun is absorbed by the water, and the water temperature goes up a little bit, but it takes a lot of that energy, so it doesn't get as hot on the coast. Okay? By the same token, in the wintertime, it doesn't get as cool because that energy which is in the water gets released to the atmosphere, so it's a moderating influence. And that's why organisms don't just boil away either. All right? So high specific heat, high heat of vaporization, same concept there. Heat of vaporization is going from a liquid into a gas. Okay? So that's primary cooling mechanisms for humans. Okay? When we sweat, okay, for that sweat to go from being on our skin, okay, to the atmosphere, it takes 540 kilocalories per gram of energy to do that. Okay, so that takes that heat away from your body. Okay, so when you sweat, as it evaporates, it takes heat away from your body. It's sometimes they're called universal solvent because it dissolves so many things. Again, because of the polarity, okay, anything which is polar, it can dissolve because the positives surround the negative parts and the negatives surround the positive parts of whatever it's dissolving, like salts and so forth. Two terms you should know, hydrophobic and hydrophilic. Hydrophobic means water hating. Okay, so things like oil, which have a lot of nonpolar bonds, CH and CC, they're hydrophobic. Okay, they don't dissolve in water. So oil and water, they don't mix. Okay, because they're not polar. Okay? Hydrophilic means water loving. Okay, so things that will dissolve in water. So those are other water molecules which have polar properties. All right. Talk about acids and bases. I'll talk more about this in the PowerPoint. But acids, of course, anything that produces hydrogen ions. Bases produce hydroxide ions. Okay? So that's when they're put into water. Right. So that level is measured by pH. Okay, so pH goes from 0 to 14. 7 is neutral. Anything below 7 would be acidic. Anything above 7 would be alkaline or basic. Okay. For organisms, they have to stay within a pretty small pH range. Okay, so to do that, we have buffers, and the key one is this carbonate buffer, okay, or bicarbonate buffer, which we'll talk about in more in the PowerPoint.